A2 Maths, resolving forces. Okay, what I'd like you to do is have a quick read of those two questions and see whether you can think about finding the resultant force acting on this particle just there in the middle. All right, it's got three forces pulling off it. And can you find the magnitude and direction of the resultant force acting on the particle? Okay, so some of you might be able to do it straight away, in which case you can get on with it. Some of you might want some extra hints, in which case I'll give you some extra hints as soon as you unpause. Okay, so let's have a quick look at what they're actually asking. We want to find the resultant of all three of these forces that are pulling at different directions on that particle just there. Okay, we need to find out what's actually going to happen to that particle. Imagine it was like a three-way tug of war. They're all pulling on this particle. Where would that particle end up going? Now, the way we do this is by looking at the I direction and the J direction separately. So what we can do is we can look at just the forces acting in the I direction and just the forces acting in the J direction. Now, if we could do that, that's what we mean by resolving the forces. So we're going to resolve in the I direction first of all. So we're looking at all the forces that are going in this direction just here. Okay, we can ignore anything going up and down. We're just looking at forces going left and right. So that's resolving the I direction. Now we know that one was 5, 3, so it's 5 across, 3 up. We know this force just here is 2 back and 4 up, so we can put that on. And this one, as you can see, is just 3 downwards. It's just like someone pulling straight down with a force of 3. So what I can do is I'm just getting that. You can do that in your head. You don't have to write it all out. Just so we've got an understanding that the vector 5, 3 looks like that. The vector minus 2, 4 looks like that. And the vector 0, minus 3 looks like that. And what this allows me to do is just visualize what forces are acting in this direction and what forces are acting in the J direction. Now, if I just consider the forces acting in the I direction for a minute, I can see that I have 5 pulling this way and 2 pulling that way. And again, if you consider this like a tug of war, someone's pulling with a force of 5 newtons in that direction, and someone's pulling with a 2 newtons in that direction, then you know that particle is going to be moving this way as the 5 is greater than the 2. And we can say, because it's 5 pulling that direction and 2 pulling that direction, it's going to end up with a force of 3 pulling in this direction just here. So you've got the 5i minus the 2i equals 3i. And that's assuming that this direction here is positive. Okay, so we're assuming that that direction is positive, going from left to right. Right, let's have a look at the J forces, the components of the J's. So we can see that this one was up 3, this one was up 4, and this one was down 3. So if you consider what's happening to this particle here, you've got two forces pulling upwards, one of force 4 and one of force 3, and one force pulling down with a 3. So we know that particle, if you imagine that you were on there, because you've got a total of 7 pulling up and only 3 pulling down, you're going to end up going in an upwards direction with a force of about 4 newtons. So we can see that we've got the 4 minus the 3 pulling down plus the other 3 pulling up equals a force of 4 pulling upwards in the end. So what I can do is I can just put those two together, 3i and 4j. I could write it as 3i plus 4j if I wanted to, or I could write it back in vector form as 3, 4 newtons. That is its resultant force. It's going to head off in that direction when those three forces will pull in it. It's also worth noting that you don't have to separate them out. You could actually do it straight away in vector form. If you just added the 3 vectors together, then you end up with the resultant vector as well. And most of you will find this a lot easier to do. You do have to understand about the forces acting in the I and the J, because later on we're going to be resolving not just in I's and J direction, but we're going to be looking at slopes and things like that. So it's important to understand how to resolve. But when you do have vectors, it's also worth remembering that you can just add those 3 vectors together, and that would get you your resultant vector. Okay, which is in this case a lot more efficient. You just add all 3 of them together and you get 3, 4 newtons. Okay, so what's the second bit on about then? What's the magnitude and the direction of the resultant. In other words, how big a force is pulling in that direction, and what would the angle be? Okay, so what's the magnitude of the force pulling in that direction, and what is the angle it's pulling at? So again, pause there, have a go calculating that yourself, and then when you're ready, you can move on. Okay, so let's have a quick look at how we work it out then. And of course, we work it out using a mixture of Pythagoras' theorem to work out the magnitude of it, and we can use some basic trigonometry to work out the angle. So in this case, the magnitude of the resultant force is going to be 3 squared, 4 squared, square rooted. So we can see that's going to be a magnitude of 5 newtons pulling in that direction. And the angle it's going to pull at, I can use tan, alright, although I could use cos or sine if I wanted to. Tan to the minus 1 of 4 over 3. And so it makes sense to be an angle of about 53.1. Just be very wary. We've got a nice angle there that's pulling from the positive number line there, from I around to that. So you need to be aware of where it's coming from. If this was a bearing, of course, you'd have a north line and you'd have to read off from your north line. So just be aware about where you're measuring your angle from. In this case, it's from the eye line. The other thing that's important is, of course, if your arrow's pointing backwards there, always consider that you're going past 90 degrees. So you're looking for an obtuse angle in that direction. Underneath, you might be looking for a reflex angle, going all the way past 180. So just be very wary about where your resultant force's direction is and how to calculate that angle. Okay, so grab your notebooks then, please. And let's have a look at a similar situation, but this time, instead of putting them in component form, I'm looking at them in magnitude and angle form. So grab your notebook, just do a quick sketch of that drawing. And the question is, what is each of the forces in component form? So you can write the question and we'll look at putting the answer in your notebook. If you want to pause there, give you a chance to write it down and feel free to actually have a go yourself at working out the answer. Okay, so let's see if you manage to put these into component form then. So for each of these, I'll do one at a time. I'm going to start with the 8 newtons pulling off at an angle of 40 degrees from the negative I line. Okay, so I'm looking at that. If I look at these two in component form, I need this magnitude here and I need this magnitude here. So I'm looking for those two. And don't forget, you can calculate these easily. They're just going to be 8 sine or cos 40. And the hint I always say is this line just here is connected. So that's going to be the cos, 8 cos 40, because that one's connected. Whereas this one is separate. So this will be the 8 sine 40. But it's just basic GCSE maths. So I'm sure you can work them out using your trigonometry skills. So 8 cos 40 and 8 sine 40 just there. So there we go. 8 cos 40, 8 sine 40. So once I've got both of those, you can leave them in that form if you wanted to, or we could write them as a decimal. If you are going to write them as a decimal, just be wary about not rounding too early. So in this case, I would probably think about sticking with just 8 cos 40 and 8 sine 40. But if you want to do it as decimals, that's fine. Just be very wary about the top one. You notice that I've automatically put a minus sign in, and that's because I considered what is the actual direction here. Because of course, if you didn't put the minus sign, 8 cos 40 would go in this direction, and then 8 sine 40 would go here. You'd have that basically mirror imaged over here. So be careful. Consider the direction you're traveling. You're going back, so that's minus 8 cos 40, and you're going positive, that's 8 sine 40. We'll think about that when we come to this next one. If you want to put in decimals, that's fine. There you go. So it's decimals. So we're traveling about 6 back and about 5 up. Okay, so I've put that in component form just there. I could do the same with the other one then. So the 7 newtons acting as an angle 60 below the eye line, the negative eye line. So I've got this. How's that help me? Well, now I can work out these two bits. So this one's connected, so it's 7 cos 60, and this one's separate, so it's 7 sine 60. I need to go back, 7 cos 60. I need to go down, 7 sine 60. So I can fill both of those in. I can get my calculator and I can work them out. Notice that you're going back, so it's negative, and you're going down, so it's negative. And of course, the answer to that is going to be roughly minus 3.5 and minus 6.06. So I've calculated both of those forces in component form. I know how far back, I need to know how far down I go. I can put them in either form. And you need to be confident to be able to split the forces between the vector form and the component form. Okay, so the vector form and the magnitude and direction form. Okay, so now we've got both of those. Let's have a look at the question. Three forces are acting on the particle, so it is in equilibrium. Now, I don't blame you for thinking that equilibrium means that it's stationary. Now, it doesn't mean it's stationary. What it means is it's not accelerating. Okay, so you can have a particle in space, for example, that's moving at a constant velocity, and therefore it's in equilibrium. It's very easy to make the mistake that equilibrium means you're stationary. You don't have to be. If you are stationary, though, you are in equilibrium. Okay, so stationary implies equilibrium, but equilibrium does not imply stationary. All right, so we've got that. We know this particle is moving with a constant velocity. There is no acceleration acting on that. Why is that important? Because it's to do with Newton's rules, which we'll come back to in a second. Okay, so what does equilibrium mean? Just mentioned that. It means that the resultant force is equal to zero. There is no acceleration. So the resultant force is acting on the particle is equal to zero. It's worth just getting that back down in your notebooks and highlighting it. So that's quite handy to know. It means that if we find the resultant of all three of these forces, so that one there, and that one there, they should all balance out. They should all equal each other. Now I'm going to do this one with vectors to make it easier. If you want to do it just with i's and j's and resolve in the I and j's direction, it's up to you. Okay, if you're going to do i's and j's, it'll be this one here going across in the f direction. The f in the I direction will be 6.13 and 3.5. They have to balance each other out. How do we work out the up part for f? Well, it'll be the 5.14 added on and then minusing that 6.06. But it's easier to think of it in vectors rather than trying to do it in i's and j's and having to think, how do I split this f up? All right, it's easier just to say, right, I'm going to add these two together. I'm going to add this vector f, which I'm not sure what it is. That's what I'm trying to figure out. I could do a bit of rearranging, so I can take that to that side and take that to that side, and that's going to leave me f must equal 9.63 and 0.92. And again, you can see that makes sense if you add those two together there, and if you take those two or look at the difference between those two to work out 0.92. Okay, either method is fine. Okay, so what I'd like to do is just have a go at completing the exercises on 1.3 and 1.4. Right, so that'll be looking at resolving forces and also using equilibrium. And then once you've had a go at those exercises, you can move on. Okay, so let's have a quick look at this everyday life situation. A dog has a mass of 22 kilograms and an owner's taking for a walk on a smooth frozen pond. Now, what's important about the word smooth frozen pond, or certainly the word smooth would have been more than enough. Okay, so what would it mean to be smooth? And so we use the word smooth in maths to represent something that does not have a frictional force. There is no friction acting between the dog and the ground. So it means the dog can move smoothly and there will be nothing else stopping it from moving on the ground. So that's an important word there, smooth. It doesn't matter so much about the frozen part. It just makes it a bit more realistic that if it's on a frozen pond, for example, there wouldn't be any friction. It would just slide along. Okay, so the owner's got him. He's trying to pull him along this ice, and the dog's reluctant to go. He's just stood there or sat there, whatever you like. Okay, so what I'd like you to do, please, is just have a go at drawing the forces acting on the dog. Now we know there's no friction. What forces are acting on the dog? So pause there, have a quick sketch of your force diagram. Okay, hopefully you didn't spend ages trying to draw a fabulous picture of a dog. You can just use a block to represent your dog. Okay, so there's my dog. You can ignore the picture. We're looking at just that block, like it's in an ice cube. Okay, so what I'm looking at is definitely a force of 17 newtons being led off at 50 degrees. So there we go. There's a force of 17 newtons just there being pulled off at 50 degrees. If that's the only force, and it might be the only force you drew on your diagram, but if that's the only force acting on that dog, what's going to happen to that dog? You know, what would actually happen to that dog if that was the only force? Okay, so have a think about that. Okay, if we tried to resolve it then, and we thought 17 newtons off at 50 degrees is the only force, what's going to happen is that dog will travel off in that direction with a force of 17 newtons. It would actually go exactly in line with where the owner is pulling it up. And of course it would carry on going in that direction until it goes into outer space. So clearly we're missing something. There's got to be a force that's acting on this dog that we've forgotten about. And the answer is its weight. Okay, the dog has a mass of 22 grams. Okay, so it's definitely got a mass of 22 grams. Well, that means that it has a weight. Be careful, weight and mass are different. A mass is a scalar quantity, whereas its weight means it's pulling down towards the center of the earth. So it has a force pulling that dog down, and the force pulling it down is its weight, and you measure weight in newtons. How do we calculate its weight? Well, it's very easy to calculate. It's going to be its mass times gravity. Weight is always mass times gravity. That's why when you're in space, you are weightless. You are not massless. You still have a mass in space. You are weightless though, because you don't have an acceleration pulling towards the center of the earth. Okay, so in this case, we can work out the force that the dog exerts on the earth. If it's got a mass of 22 kilograms, it's going to have a weight of 22 times gravity, and we'll write that as 22 G. Now 22 G is not 22 grams, be careful. It's 22 times whatever gravity is. And in maths, that's often 9.8. Sometimes in exam questions they say gravity can be 10. Sometimes you might have it as 9.81. All right, so if you do physics, they use 9.81. So be very wary. That is not 22 grams. That's 22 times 9.8. That's its weight. Okay, so that's fine. Now we've got the owner pulling off with 17 newtons. We've got the dog pushing down on the earth with 22 G newtons, 22 times 9.8 newtons. So if they're the only two forces acting on it, what's going to happen to the dog now? So pause and have a think. What would happen to the dog now? Just mention this. It's just flashed up in red. If you haven't noticed, this is Newton's second law, right, which is something you need to recognise. It's the only formula you need to learn with forcing. F equals ma. So anytime you do anything with forces, learn that formula just there. Force equals mass times acceleration. And in this case, the force is weight. The mass is clearly the mass. So that bit's fine. And the acceleration is gravity. The same as if you jump out of a plane, you accelerate down towards the earth, and you're accelerating due to a gravitational acceleration. Now in this case, the acceleration is just g. So it's just a reminder, quick flash up to remind you that we are still using F equals ma. It's not a new formula, it's still F equals ma. Okay, so back to my question then. If the owner's force from the lead and the weight of the dog were the only forces acting on that dog, what would happen to the dog? Okay, try writing the word dog as many times as possible. So the weight of the dog, the force from the owner's lead, what actually happens to that dog then? So think about resolving, think about what we did before. All right, think about all the forces acting on a dog. Is it in equilibrium? Is it just sitting there? Well, it's not, is it? Because you've got force pulling in this direction, which you'd expect it to do. You'd expect the dog to be skating along this ice. We've got a bit of force going up here. All right, 17 sine 50 separate, so it's 17 sine 50 pulling up. But you've got 22 G pulling down. So even if G was 1, you've still got 22 pulling down. So this dog is going to end up doing that. That's what's going to happen. And the same reason that when you're stood on the floor, you don't just fall through the floor. Right? There is another force acting on this dog. Right? So we know there's a force from the owner pulling it. We know there's a force pulling down, which is to do with its weight. There is also another force, and that is called the normal reaction force. Whenever you're stood on the floor, you are pushing down with a force which is to do with your mass. The ground is pushing back on itself, or back on you, sorry, and it pushes back with an equal but opposite reaction. And in this case, we put that down as what we call the normal reaction. Sometimes we use N, sometimes we use R. Okay, so you can use either of those two letters. And it means a normal reaction force. The reason why it's the word normal in there, because it is perpendicular to the floor. So in this case, the floor goes in that direction. The normal reaction force is perpendicular. Be careful if you're stood on a slope. You'll see this later on in another question. If you're stood on the slope, the normal reaction force will be in that direction, perpendicular to the slope. Okay, it does not just always push up. That's where the normal comes from. Okay, so we've got our three forces. Right, we can see now that because the reason why the dog doesn't just plow straight through the ice is because the ice is pushing back on that dog to stop it coming through. Clearly, if the dog weighed too much, it would break through the ice because the normal reaction wasn't strong enough. So you can actually overcome the normal reaction and you can actually fall through the ice if your mass is too high. Just to remind you, Newton's third law states that fact. Okay, so although you're not going to be tested on knowing and being able to list off Newton's laws, you are expected to have an understanding of them. So Newton's second law is to do with F equals ma, and Newton's third law is that any force always has an equal but opposite reaction force. Okay, so I think we're pretty much there, aren't we? There's nothing else acting on this dog. We've got the owner pushing up, we've got this weight pulling down, we've got the ice pushing back on our dog. So what we can do now is we can actually calculate the normal reaction force. We can calculate this R value, and we can also calculate the resultant force acting on the dog. We can see what's going to happen to our dog. Okay, that's what we're going to do now. So now we've figured out all our force diagram, we can now do the bit of maths we did early on in the lesson with our force diagram. We're going to assume that dog is a particle, all right? It means that we don't have to worry about surface area or the dog spinning in the air or anything silly like that. We can just assume the dog is a particle. And we can resolve in both the I and the J direction. Now, it's quite common for people to make the mistake of thinking that R is always the same as the weight, okay? Because it looks like it's just opposite to it, doesn't it? 22g pushing down, 22g pulling up. Now, that would normally be correct if there wasn't other forces acting on it. Now, because this force is acting on it, just have to think what's happening here. The owner is actually pulling the dog up a little bit, okay? Not much, but the owner, by pulling the lead at this angle, is actually making the dog go up in the air slightly. That's not leaving the ice, but it means that some of the dog's forces pushing down is counteracted by the owner, which means that the R value is not going to be exactly the same as the 22g. Alright, because some of it's been taken up by the owner. So the R value can be less. And this is important later on when we come back about friction. So how do we actually figure that out though? Well, if we're resolving in just the J direction, we know that we're only looking at the forces pushing up and down. So in this case, what forces are pushing up? Well, we do have the 17 sine 50. The owner is pushing up with a force of 17 sine 50. The dog is pushing up, or sorry, the ice is pushing the dog up with a force of R, and the dog's weight is pushing down against the ice with 22 times G. So we can put all those facts in. Notice I'm putting 9.8 in for my gravity. That's where that's come from, 22G. I've got minus that because I'm taking the up as a positive direction. It doesn't matter which you choose as your positive direction as long as you are consistent. Okay, so I've decided that up is positive. That means the R is positive. That means the 17 sine 50 is positive, but the 22G is in the opposite direction, so that's negative. Okay, if you decide to do the other way around, it will be negative, negative, positive, and you get the same answer. Okay, so just be careful when you're resolving to consider which direction is positive. Okay, so why does that help? Well, actually, look, R is the only one you don't know. You know that. You know that. So a bit of rearranging, a bit of calculator work gets you an R value of 202.6 newtons. So there's my R value. That's what the force of the ice is pushing up on the dog. Okay, well, what about how the magnitude or the resultant force of the dog itself? Well, if you look at the I direction, there's only one force actually acting in the I direction, and that's the owner. The owner is pulling that dog along with 17 cos 50 as a force. The dog's trying to sit there and not move, but the owner is overcoming that with a force of 17 cos 50. And because nothing else is acting against him, that is the answer we're looking for. The only force acting on that dog in an I direction is 17 cos 50 if I take that as positive. So what does that mean then? Well, the dog is going to be moving in that direction with 10.9 newtons. Just so you notice, I set the J to equal 0. And the reason for that is because the dog isn't moving up and down. It's not leaving the ice. It's not ploughing into the ice. So in some ways, the dog is resolving equal to 0. Okay, those two forces are balancing out. The dog is not in equilibrium because it's moving in this direction. Okay, it will have an acceleration in that direction, but it is definitely not moving up and down. So that's why those two equaled a resultant of 0, whereas left and right equaled a resultant of 10.9 newtons. So a force of 10.9 newtons in that direction just there. Okay, and you can go on and you can work out its acceleration if you wanted to, because you could use F equals ma. Now you've got a force and you've got a mass. You could actually work out the acceleration of the dog in that direction if you were required. Okay, so just grab your notebooks then, please. I would like to have a go at writing this question down. There's a fair bit of writing. You can either take down the key facts, or you can just take your time and write it out. Then once you've wrote it out, I'd like you to have a go at reading it and doing what it's asking, which is, in this case, trying to draw the force diagram. Okay, so what makes this question a little bit tougher than some of the other questions is the fact that this box is sat on an inclined plane. It's not just the situation we had before with the dog that sat on a flat plane like that. It's inclined. So the first thing I'm going to do is just draw that incline in. So there we go. You do not need to get a set of protractors and make it exact or anything silly like that. Just a rough sketch showing two straight lines. Also, you don't need to show it as a hill. It's not a parabola shape or anything like that. You could just show that angle of 25. Now the box is sat on that slope, so I can stick the box on the slope. And I use that sort of rectangle shape regardless of what it is. In this case, it is a box, so it makes sense. Now let's say that box is just sat there. Okay, that box is just sat there, there's nobody touching it. What are the forces acting on that box? Now we know for a fact that one of the forces definitely acting on that box is going to be its weight. And that's to do with its mass of 89 kilograms. Now the reason why we're talking about weight and not mass is because we're talking about a force diagram. Mass is not a force. It needs a direction to make it into a force. It needs a direction to make it into a weight. So, which direction is that box being pulled by gravity? And it doesn't get pulled down the hill by gravity, although if it does slide down the hill, it's to do with gravity. And it doesn't get pulled perpendicular to the plane by gravity. It does exactly the same as anything else. It gets pulled directly downwards by gravity. So even though it's on a slope, you would still put its weight vertically downwards like that. And it has a weight of 89 times gravity. That's why it's being pulled straight down towards the centre of the earth. So that's the first force you can put on. All right, so you can put the other ones in any order, but that's definitely one of the forces you need to put on. Now, what stops this box just ploughing straight through the incline? Well, there must be a resultant force. And this is where people often make a mistake. They put the resultant force opposite to gravity, and it's not. It's a reaction force with the plane. Now, because the plane is in this direction, the normal reaction force will be perpendicular. So we can draw our force going perpendicular to that plane. So gravity might pull it straight down towards the centre of the Earth, but the R value always pulls out perpendicular to this plane. Okay, so that's the first two forces. Now let's consider the other forces then. What's stopping this moving down? It would slide straight down. Okay, would slide straight down there because there isn't any other forces acting on it because it is smooth. There is no friction. Okay, if that box was made out of, let's say, a very rough wood material and this was made out of some sort of sandpaper, you can imagine that box would not move, and it wouldn't move because friction's stopping it. But because it's smooth, it's like putting an ice cube on an ice plane. It would just slide straight down, and it would definitely slide straight down because, as you can see, a bit of gravity is pulling it down. Okay, gravity is pulling it down the slope slightly. So what's stopping it? Because it is in equilibrium, that means it's either stationary or moving at a constant velocity, either up or down. It's not accelerating, and all the forces can be resolved equal to each other. So what's stopping it moving down then? These two people. One of them is pushing. All right, so if someone stood here and they're pushing that box up the slope. Someone else is beyond that. They've got a rope. They're pulling at an angle of 20 degrees to the slope. So he's sort of pulling a rope like this, and he's trying to pull it up the slope. Now, I wouldn't blame you for thinking I'm going to put my arrow there with a little arrow pointing towards a box to represent the person pushing it. That's a bit messy, all right, because the arrow's on the wrong side. You always have forces coming out from that drawing. So instead of putting the force pointing in towards the box, I'm just going to have that person who's pushing up showing the force that direction. So that's the person that's pushing the box in that direction up the slope. So don't think you have to draw it on this side just because that's where the person stood. All right, he's pushing with a force, or she's pushing with a force of 20. P for newtons up the slope. Okay, so that's the first person sorted with a force of P. There's another person who's also pulling with a force of P, and he is stood about here and he is pulling this box up the slope. So I can put on there 20 degrees to the slope, and he's pulling with a force, or she's pulling with a force of P up the slope. I think that's it, isn't it? We've got the weight, we've got the normal reaction, we've got the two people pulling and pushing it up the slope, and it is then stopped. It's either stationary or it's moving with that constant velocity. It's not accelerating. So these forces must all balance out. They must all be resolved to zero because it's an equilibrium. So what I can do now is I can start to consider these forces and I can resolve. Now, as I said before, you don't always resolve in I and J. You can choose any two non-parallel, it's no good having them parallel, any two directions you like to resolve. And it makes a lot more sense in questions like this to resolve up and down the slope. Now the problem is, if I resolve up and down the slope, this angle here seems to be missing. I don't know how much, this is gravity pulling it down, so this is to do with the weight, but I don't know how much is pulling downwards and how much is pulling down this direction. Right, so I need to figure out how much is pulling, what we say, perpendicular to the slope, and how much is pulling up and down the slope. So what I'm going to do is we're going to do a bit of basic trig, a bit of GCSE trig. So what I'm going to do is just give you this drawing, and I want to see if you can figure out what that angle is there, or what that angle is perpendicular to the slope. So just pause there and have a go at that GCSE work and see if you can figure it out. I want to know the angle perpendicular to the slope. So not that angle there, that's parallel to the slope. I want the one that's perpendicular, so it's just there. Okay, let's see if how you were with your geometry then. So the first thing I'm going to do is just draw the line they're talking about. So we're talking about this line just here, the perpendicular line to the slope. So that's what I'm looking for. All right, because if I can figure that out, I can figure out the angle I want. Okay, Right, if I've put that in, now I can just do, because that's quite nice, that's 90 degrees there, there's 90 degrees there. I can just use some general skills with triangles because I know that angles inside triangles equal 180. So if that's theta, and that's my general triangle, and that's 90 degrees just there, I know that this one will have to be 180, take away 90, take away theta, 90 minus theta. Okay, I know that for a fact. But I also know that this is 90 degrees. So therefore, this one, and this one must add together to make 180. And the only way that would be possible is if that angle there is also equal to theta. Now that's a really important fact that we've shown with a bit of GCSE trig. It's a really important fact because that means that every single time I want to work out the components or to do with weight, I always use that fact. I draw a dotted line perpendicular to the plane. So I draw my box on my force diagram. I could draw dots going off perpendicular, and then the angle between that perpendicular line and my weight pulling down is always the same as the slope. So if the slope is 20 degrees, that'll be 20 degrees. If the slope is 48 degrees, that'll be 48 degrees, and so on. So knowing the slope means you know the angle between weight and perpendicular. And I'll show you why that's important. So just pause there if you want to take any more notes. So what I can do is I can put that on. And why that's important is now, if you look at your diagram and you're thinking about resolving up and down the slope, I can do this now because I've got everything in terms of, I've got the angles for everything. So we're going to think about up the slope first of all. So the reaction force P. So I apologise, not up the slope, we're going to go perpendicular to the slope. So if I think about resolving the forces, that's what it's saying here, up and down the slope or perpendicular slope, it doesn't matter which one you pick, then we can start to see if we can figure out both the P value and then the R value. So what I'm going to do is I'm going to resolve parallel. So imagine that I'm only looking in this direction. All the forces acting in this direction. And what's good about going up the slope as opposed to just going up and down, if I went up and down, I'm going to have to figure out R, I'm going to have to figure out the other P's, it's going to be right messy. So it's better to go up and down the slope. And the good thing about going parallel to the slope is that the normal reaction force is always cancelled out because it doesn't act up and down the slope. The whole point of the normal reaction force is it is perpendicular to the slope. So I can ignore the R value. It doesn't come into it at all. So what that means is what forces are parallel to the slope? Well, certainly this P is. All right, the full P is pulling up the slope perpendicular. There's also, that's the person pushing that box parallel to the slope. That P is parallel all the way up. The other bits though are a bit of this one here. So this person who's pulling at 20 degrees, they have got P cos 20 pulling up the slope. So that person there has P cos 20 pulling up the slope. So we've got one person that's got the full P, one person that's got P cos 20, and also what's stopping you pushing up the slope? Gravity. Now the gravity that's stopping you pulling up the slope is not all of it, because it's not just going straight down towards the centre of the earth, it's got just a bit of it, is this part just here. And that's the bit that's separate from the 25, so it's 89g sine 25. So let's just put that down and make sure we're happy. We've definitely got the P. All the P is pulling up. We've also got this part here of the person that's pulling it up with a rope. So that's the P cos 20. We've also got the 89 G sine 25. And let me just explain what we've done there, because you might prefer to do this or you might prefer to have it equal to 0. It's up to you. You can put all the forces that are in one direction equal to all the forces equal to on the other. And you can do that because it's an equilibrium. Okay. What most people prefer to do is do what we did before, which is push all the forces in that direction as positive, any forces in this direction as negative, and then you'd rearrange to get to this afterwards. Okay, but it's exactly the same. But if you prefer to do P positive, P cos 20 positive, that one negative, because it's going down the slope, that's fine, equals 0. Right, so what can I do then? Well, I can certainly do a bit of factorising. I can put that together, get 1 plus cos 20, and I can divide it by that, and I'm going to get these sorts of numbers coming out. So, or you can do it with just working out cos 20, do 1 plus whatever that is, and so on. Then what? I get P equals 190 newtons. So you've calculated what force must have been pulling that box to keep it in equilibrium, all right, by those two people. If you need to work out the normal reaction force, it's unlikely you will do, but if they want you to work out the normal reaction force, you could do that now. Because now you know what P is, and you resolve perpendicular to the slope. So let's have a quick look at that. All right, so yes, I said that about not having any part of it. So if we're looking at resolving perpendicular to the slope, what are the forces acting perpendicular? Well, we definitely got the full R. That's definitely pulling, all of it is pulling up that slope. Okay. We've also got a bit of this person who was pulling with a rope. They're lifting that box slightly off the slope. Okay, so that's P sine separate, sine 20. Putting up there. What else is acting perpendicular slope? Oh, there was gravity as well, wasn't there? So weight of the box due to gravity. So it's this part just here, and that is your 89G cos 25 because it's connected to it, so it's cos 25 there. Notice the person that was pushing the box up the slope doesn't come into this at all because they are perpendicular to that, so they didn't have any force pushing up and down. We can ignore them. The same as we ignored R in the previous one with the parallel, we can ignore the person that's pushing up the slope because they are perpendicular to each other. Right, so a bit of rearranging. Don't forget we know what P is now. We can put the 190 in. All right, we'll definitely put that in and rearrange it, and well done if you got R equals 725 newtons. So that's an example of one of the more difficult type questions because you've got to consider all the angles that go into it. So just pause there if you need a bit more time to write anything down. Now you've got lots of questions, lots of exercises to have a go at. My advice is to take your time with it because they can ask it in lots of different ways, and on a whole it is all about drawing that force diagram. If you can draw the force diagram fully, then you should be able to resolve it afterwards like you did in the previous exercises.